Hey guys, so last video for this week. I'm not going to do a video for the assignment, but you should go take a look at it. I'm going to ask you to do some text classification, and I'm giving you a corpus called Reuters 21578. It's a corpus, an old corpus that I worked with as a student, but is still used for benchmarking. And it's Reuters is a newswire service. So it's 21,578 news stories from the Reuters newswire service. And each news story has a bunch of labels attached to it, mostly topic labels, but also place labels and things like that. So a document might be labeled economics, wheat, because it's to do with farming and wheat production. So it might have the wheat label, the economics label, and the Canada label, for example. So each of these labels, wheat, economics, Canada, as well as all the other labels. There's one called EARN, E-A-R-N, one called silver. There are hundreds of them. Each one of those is a classification task. So the task with this corpus is to learn a bunch of different theories, one for each label, and then go through the corpus and label the documents correctly or incorrectly as documents related to wheat, documents related to silver, documents related to Canada, and so on. So you train a set of binary classifiers for it. Each classifier is for one label. So it's either wheat or it's not wheat. It's either silver or it's not silver, and so on. So that's the default corpus for you to use. I'm open to you guys using other corpuses as well, but I've given you some tools for that one. Okay, so in information retrieval, which is what we're doing here. Information retrieval broadly is the user searching for some information, and you search this huge, enormous corpus of information, and you return the relevant things. So like a Google search is a classic case of information retrieval. But text classification, you can think of it as a special case of information retrieval as well. So I might say, I want all the documents related to silver. And a machine learning algorithm may have gone through those documents and put the silver label on some of them and not on others. So if you search by topic using the restricted set of class labels, in a way it's very similar to doing a Google search. You want to retrieve the relevant documents. And one issue that information retrieval has, which it's not just an issue related to information retrieval. It's an issue that comes up whenever you have a really unbalanced data set. And this just happens to happen a lot in information retrieval. Like if I'm doing a Google search for, I think one of my examples here is judo. I'm doing a Google search for judo, the martial art. There are billions and billions of documents on the internet. What proportion of them are going to be relevant for this search? Probably almost none, right? So it's a really unbalanced data set. And the Reuters corpus that I've given you is like that as well. Here's an example down here. So the most frequent label in the Reuters corpus is earn. So it's about earnings, I guess, like financial earnings. But only 18% of the documents in that corpus have that classification applied to them. So 82% should not get the earn label, 18% should get the earn label. There are 120 possible topics. 55 of them, there's only 10 or less documents with that label on them out of the total 21,578 documents. So it's a super unbalanced data set, but that's not strange. That's ordinary for information retrieval, right? So think about searches for whatever your favorite topic is. What proportion of all the billions of documents on the internet are going to be relevant to that one search? Very, very, very few. So why does this cause a problem? Well, because so let's take this example uses the silver label. So you've got let's say we trained two different classifiers, and their job is on the Reuters corpus, which has 21,000 documents in it, and they're trying to learn silver or not silver. So this document is relevant to the topic silver. Presumably this is about finances and financial markets and silver trading and precious metals trading and stuff. There's only 37 documents in the whole corpus that have the label silver. So almost none. So classifier A doesn't actually do any work at all. It doesn't retrieve any documents. it always says not silver. It never puts the silver label on any document. But because silver appears so infrequently, if we just measure its accuracy, it's right 21,541 times out of 21,578 times. That's 99.8% accuracy for doing no work at all, for just ignoring the document completely. Whenever I give it a document, it just says, nope, not silver, and it achieves 99.98% accuracy. Now the next one, the next classifier, it outputs silver for 100 documents. So it predicts out of 21,578 documents that you give it, it predicts that 100 of those are about silver, but it's not very precise. So it's correct only 30 times out of those 100. So it produces 100 documents and says these are about silver, and it's only right 30% of the time. If you compute the accuracy, so it turns out it's correct this number of times out of 21,578. So it has a lower accuracy, 99.6% instead of 99.8%. But whereas this classifier did no work, this classifier does retrieve 100 documents. And sure, it's not super accurate within those 100 documents, but if you think about what it's done for us, it's reduced our task quite a lot. It's reduced our task from searching through 21,578 documents to searching through 100 documents. Now we just have to look at 100 and figure out which ones are relevant, and 30% of them are going to be relevant instead of 0.2%, which would be relevant in the 21,000 case. So it's done some work here. It's retrieved, it's actually found 30 of the 37 documents correctly. So it's missed 7 documents, and it's given us 70 that are not really relevant. But it's done a lot more work in some sense than this, and that work is not captured by the accuracy, because if you go by accuracy alone, this one looks better than that one. So I hope that makes sense. So we really, for most of these tasks, really, we can't really use accuracy. Accuracy is not going to be helpful as a measure of information retrieval tasks. So what we do instead is we come up with, we make 2 other measurements. We don't use accuracy so much. We use these measurements called precision and recall. So if you take a look at classifier B here, classifier B has recalled or found 30 out of 37 documents. That's its recall score, 30 out of 37. And its precision score, we look at how many it recalled. It chose 100 and labeled them silver. Its precision is 30 out of 100. So those 2 scores together, recall is actually pretty high. Recall is the measure of how many of the correct documents did it find. It found 30 out of 37 correctly. So it has a high recall, probably around 80% or something. But its precision was a little low. Its precision of the documents that it retrieved, only 30% of them were relevant. So its precision is low, its recall is quite high. Those are the 2 measures we use, precision and recall, sometimes abbreviated P and R in the literature. This thing over here recalled 0. Its recall is 0. So right away, you know, this is not doing very well. And its precision is actually an undefined number. It's actually 0 over 0, which is undefined. So when you look at precision and recall, this one is doing way better. This one found 30 out of the 37 relevant documents. This one found 0 relevant documents. So it gives us, in a way, it gives us a better view of what these algorithms are actually doing. So here's how it works. Here's how precision and recall work. You have to measure now what we were counting before. When we're just doing accuracy, we have to maintain 2 counts, correct and incorrect, or correct and total. And then we use those to determine accuracy. If you want to do precision and recall, you have to create what's called a confusion matrix. This is actually a technical term, the confusion matrix. There are 4 numbers, there are 4 counts to keep track of. So if you think of this as a matrix, as a table, across the top we have our predictions, and down the side here we have the real answers. So when we're measuring performance, we know what the correct answers are when we're measuring performance. So we make a little graph like this. So the number A represents the number of times we said it was a silver document and we were right. And then the number C represents the number of times we said it was silver and we were wrong. And then over here, B represents the number of times we said it was not silver and we were wrong, because it really was silver. And D represents the number of times we said it was not silver and it was not silver. So A and D are the times that we were correct. B and C are the times that we were wrong. And in an unbalanced data set, D is going to be massive. So D is going to be very big. Most of our numbers are going to be down in this column here because we've only got 37 out of 21,000 documents that are silver. So these numbers are going to be small. These numbers are going to be big. And if we're doing things well, this number is going to be the biggest. Okay, so if we look at our two classifiers here, the first one, which did no work, this one always said not silver. So it never predicted silver. So it was correct 0 times, and it was also wrong 0 times because it never predicted silver, so there's nothing here. Here, where it predicted not silver, it was wrong 37 times. There are 37 silver documents that it got wrong, and this is what's left over. Okay, so it's recall. So anyways, so that's that. And then over here, the other classifier predicted 1 100 times. 30 times it was correct. 70 times it was wrong. It predicted 0 the rest of the times, so 21,408 times, and it was wrong 7 out of those times, and it was correct 21,000 times. So if you look at, if we're just doing accuracy, we do this number plus this number, which is the correct. Oh, I think that's a typo there. That should be a 401. I should fix that. I'll try to fix that and post a new version of this. So if you add up those two numbers and then you want to do, accuracy is the number of times you got it correct over the total number, which should add to 21,578. So it's the number of times we were right, this plus this over the total number in the document. Same over here, this plus this over the total numbers. This comes out to 0.998, so 99.8%. This comes out to 0.996. So on accuracy terms, again, this one doesn't look as good. Now precision is a measure of all the things you pulled out, all the documents you retrieved and said were silver, how many times were you correct? So we're looking at 30, the number of times we were correct, over the total number of documents we said were silver, 30 plus 70, which is 0.3 over here, and over here is not a number because it's 0 over 0. And then recall is we look at this column, with this row here, we say, okay, of the total number of actual silver documents, what proportion did you say were silver? So I was correct 30 times out of the 37 possible documents I was trying to recall, I was trying to find, and that gives me a 0.811. So precision is 0.3, recall is 0.811. Over here, recall is 0, right? Because I got 0 correct out of the 37 that were actually silver. So these are the formulas over here. Accuracy is, oh, this is wrong too. Okay, I'm going to fix this as well. Accuracy is A plus D over A plus B plus C plus D. It's the correct predictions over all the predictions, over everything in the chart. Precision, let's make sure I got these right too, is A over A plus C. That's correct. Recall is A over A plus B. Precision and recall, the one big thing to notice about them is that they ignore this. They ignore the case that's really easy to do well on, which is the case where it's not, where you correctly predict that it doesn't belong in the class. Because so many of them don't belong in the class, it's really easy to get that number good. So we ignore that for precision and recall. Okay, so by these measures, classifier B did a lot better than classifier A. All right, so what you're going to need to do is in your code, instead of just, you're going to look at your predictions and you're going to look at your, so wait, let's take a look over here. Let me get a whiteboard up. Okay, so what you're going to do is you have, oh, there we go, that's nice. Look at that. Oh, that didn't work so well. Let's try this. Nope. Come on. It's trying to be too smart for its own good. Okay. Oh wait, how about that? Oh, there we go. Okay, so this is predicted a 1. This is predicted a 0. This is the true class was 1, and this is the true class was 0. So these numbers are A, B. Am I getting that right? Nope. A, B, C, and D. Okay? So then imagine the true predictions, the truth and the prediction. Okay? So if your prediction is, if the true labels were 0, 0, 1, and 1, and you predicted correctly for this one and wrong for this one, and correctly for this one and wrong for this one. Okay? So your system got 2 out of the 4 classifications correct. What you're going to have to do is, instead of just counting, this as 2 wrong and 2 right, you're going to have to look at these carefully and do some if statements. Say, okay, in this case, we predicted 0 and the correct answer was 0. So this, we should add 1 to our D. In this one here, the true answer was 0 and the prediction was 1. So we got it wrong. That's C. Here the true prediction was, we got it right, the true prediction was 1 and the correct prediction was 1, so we add 1 to A, and this one here is we add 1 to B. So those are your 4 cases, okay? That you're going to have to look at that in your code, and then when you're doing your calculations, once you've got the A, B, C, and D numbers here, you can simply, precision is A over A plus C, recall is A over A plus B, and accuracy is A plus C over all 4 numbers added up. Okay, and what you'll find is, it might be hard to see here, but what you generally find is that if a learning algorithm has parameters you can tweak that will alter its performance, the tweaks make accuracy just go up and down. That's what we were looking at before, but precision and recall often move in opposite directions, right? So if you are recalling more, your precision is going to go down. If this is precision and this is recall. And if you're recalling less, you're probably going to get more precise, right? So if this classifier here said that, it said that 100 documents were silver, so it got a high recall but a low precision because it made a lot of mistakes. If we can throttle it back so that, or tweak it so that now it's only predicting that maybe 50 documents are silver, probably the accuracy is going to go up, but the recall is probably going to go down. It's probably going to miss more correct documents. So there's often a trade-off between those two things. I haven't checked to see if this still works, but this is an example. Yeah, so this is an article on Uber's machine learning platform that they use to predict delivery times and how long it's going to take to get to a destination. And it's an interesting read. They use it's actually regression, not classification, but it's very closely related to classification, and they use decision trees for it. And if you go down far enough, you'll eventually find precision and recall graphs. Is this one of them? No, that's not it. Hang on, I'll find one for you. Go back. Okay. Oh, I'm over here. Oh, here it is. There's your precision and recall curve. So what they found is that this represents various tunings of parameters, and this is their trade-off. So they found that at 50% recall, they get about 70% precision, and at 20% recall, they get a higher precision. So here they get more, they miss more correct things, but they're much more precise. Here they retrieve more correct things, but they're less precise. And I think this is their line that they've decided is where they want their performance to be. So they are recalling the correct answers 70% of the time, but they're making, of the things that they are labeling, they're a little bit less precise. They're more like 50-50 precise. So then take a look at those numbers. If those seem low, that's the nature of a real-world machine learning task. Anyways, so that's it. Basically, you're going to have to add this code into your assignment. And when you do your assignment, you're going to have to measure these A, B, C, and D values like this. And then you're going to report the precision and the recall for various attempts to classify the Reuters corpus or your own corpus using naive Bayes. Okay, so that's all I need to say about this. In class, we're going to go over some of those, especially the paper and pencil exercises from the first video. Then we're going to take a look at the assignment. I'll show you the code running and hopefully give you everything you need to get up and running and get going on the assignment. So it would be really helpful to take a look at the assignment before class, and then we can talk about it, and you can ask better questions once we're actually in the live class. Okay, so I will see you in the live class.